So in this video, I want to talk about, the synthesis of ethers, retrosynthesis, particularly of ethers, epoxides, and more. So this video kind of takes in all of that into consideration. So starting with theater ethers, with sulfur, we know is oxygen's cousin. The thing with sulfur, molecules is that sulfurs actually stink. It's actually stink to work with. So a lot of people don't like working with sulfur. So if I take this molecule, for example, and I add it with some sort of alkyl, halide, chloride, here's what I get. My Let's see. So if I add this in sodium hydride, all right, which is what we know about Williamson ether synthesis, my sulfur becomes negatively charged, plus this alkyl chloride here. Again, sulfur, just like oxygen, good nucleophile, attacks the carbon containing the leaving group and expels the leaving group. And this is what we form. All right. So again, typical Williamson ether-like synthesis with oxygen's cousins. Now let's get into the meat and potato of this video. So what if I wanted to make anisole? This is called anisole. What if I wanted to make anisole? What would be my products? Well, my reactants? What would I need? Well, I have an oxygen here. I have an R group. So anytime I see this O here, sort of ether, we know, okay, well, I could probably do some Williams ether synthesis on that. So I'm going to break this bond here, right, and form this from an alcohol, phenol, plus CH3X, where X is any halogen, right? And we could treat this in basic conditions. So we could treat this in sodium hydride, which is our non-nucleophilic base. And again, our oxygen gets protonated, right? And then we form a negatively charged oxygen that attacks a methyl carbon, which is very open, and expels our leaving group. So with the synthesis forward, we could say, okay, well, we could add this with phenol plus CH3. I'm just going to choose an alkyl halide in sodium hydride, and we get anisole. All right. So notice the reason why I chose this code. I choose to break this bond instead of this, right? Because if I choose to break this bond instead, and use this as my so let's see, let's do it the other way. What if and I want to squeeze it here. What if I chose this? What if I break this bond here, right, and put it, any halogen there plus CH3, all right. See, so put any halogen there plus methanol plus methanol. Again, you could see that this chemistry would be very hard, because actually what we're doing is creating negatively charged oxygen to attack the phenol, or this aromatic here, which is just non-productive. So in this case, the only way we could have went about it is breaking this bond here. So let's look at the next one. What if we wanted to make this? So make this from any alcohol. And guys, your exams differ, so your professors might want different. So be careful to read your instructions. So what if I wanted to make this from any alcohol? All right, what if I wanted to make this from any alcohol? Well, again, this is a typical Williamson ether synthesis. So which bond I'm going to break? I'm going to break this one or this one? Well, I have to break this one. Does everybody see why? I have to break this bond. I have to break this bond and create this from an alcohol. So during the synthesis, this will be created from an alcohol plus, all I'm just going to do is replace this bond with an alkyl halide. So let's see, I'm going to replace it with bromine. And again, if I add this in sodium hydride, I get my product. Now, why I couldn't break it here and replace my halogen here? The reason being is that, notice the difference. When I add sodium hydride, my oxygen gets deprotonated and I have a secondary carbon to attack. So that's still prime for SN2 chemistry. If I do it the other way, so if I made this into the alkyl halide instead, plus OH, does everybody see why this would not work? Right, I'm actually going to get E2 chemistry here. Steric strain, right? This is a tertiary carbon. There's no hydrogens. This is just not open to attacking. So when you deprotonate your oxygen, you're going to actually eliminate and not do SN2 chemistry. So that's the reason why we only had one option, which was to break this bond here. So let's look at a couple of problems. So what if I'm given this molecule here? All right, and the directions was to make from any ether. What would be my starting materials? Well, again, remember we said ethers mostly react in acidic conditions, so we should be thinking about some sort of acid. Now, anytime you have, a molecule that two halogen, and when it comes down to ethers, when two halogens is attached to the end, that means it's coming from a ring, right? It's coming from a ring. So let's count our carbon. So we have 1, 2, 3, 4, 5. So we have a ring that has 5 carbons, but remember, from any ether, well, these two come together will actually make up for oxygen. So we get this from this molecule here. Right? So again, let's count our carbons. 1, 2, 3, 4, 5. And then this di, this diiodide here on the end, this actually makes up for the oxygen. So let's take this molecule and add it in HI, acidic conditions. Well, again, hopefully we know by now, my ether actually likes hydrogen, right? So it needs protonation. So the first thing it's going to do is attack the hydrogen and break that bond between the hydrogen and iodide. So we'll get something that looks like this. Oxygen 3 bond plus 1 formal charge. Now our iodide that has gained those 2 extra electrons is negatively charged. Is going to attack. So it's going to attack and form an alcohol. So again, let's count. We have an iodide that's bonded to a carbon, which is this carbon here. Now, how many things this has attached to it? Well, this carbon here has 1, 2, 3, 4, and this alcohol. So this carbon here has 1, 2, 3, 4, and this alcohol here. Now, again, remember we have plenty of HI in solution. So actually, this alcohol is gonna get protonation again. Because water wants to, this can't leave, so water wants to leave as a leaving group. So with that being said, just for simplistic reasons, without the mechanism, I'm going to create water's leaving group plus 1 formal charge, and then my iodide is going to attack and kicks off. And once we do that, we form the same molecule that we initially started with. So that's a pattern. Anytime you have 2 sort of halogen at the end, count your carbons and replace both halogens with an oxygen. If they're together, that means it came from a ring. So let's look at something more interesting. What if I wanted to make so let's draw that incorrectly. What if I wanted to make this molecule here? And the instructions say, okay, well, make from any alkene. How would you go about this problem? Well, we know about epoxides and we know about ethers. So here's a suggestion for you guys. Anytime you see an ether beside an alcohol, think of epoxide. Anytime you see an ether beside an alcohol, always think of epoxides. It's a it's the most general way of thinking about these problems. So anytime you have an alcohol beside an ether, think of epoxide. So let's retrosynthesis this molecule before we even do this forward synthesis. So I know, so let's retro, and this arrow just means that I'm going backwards. This double arrow here. So let's retrosynthesis this. Well, here's a pattern, guys, that you should pick up. Anytime you have an alcohol beside an ether, you could see that this is actually coming from an epoxide. So this epoxide, I could replace this whole term here with the epoxide bending upwards. All right, because again, you could see that on either end of the epoxide, those are where my two substituents are on. So any place that your two substituents are on, that is where you want to place your epoxide. So this is actually coming from an epoxide, right? So we could say this is our epoxide. So retrosynthesize it to this molecule. Say, okay, well, this is our epoxide. Well, we have an alcohol here, right? We have an alcohol here, but we're not worried about that. We're worried about the nucleophile. Now, look, remember we said epoxides react in basic and acidic conditions. Now, you want to look on the carbon that look at your nucleophile. We know that this has to come from some sort of alcohol, right? Right? Because we have an ether. So look at what carbon your nucleophile is on. Right? Is it on the more substituted carbon or the less substituted carbon? Well, your nucleophile, this whole thing here is on the more substituted carbon, which means that this has to be in acidic conditions. So again, let's count our carbons. We have 1, 2. So this is coming from ethanol, right? So if I place this in ethanol and acid plus H plus, I should get this molecule. Now the direction says from an alkene. Well, how do we make epoxides? Remember we said that, okay, well, do you agree that I could replace this epoxide? Let's retrosynthesize it some more. I could replace this epoxide with this alkene here, right? Now let's do this forward synthesis and see if everything makes sense. And we shall go through a couple more of these problems, so these problems will make sense to you. So if I take this molecule, and remember we said any alkene in some sort of peroxy acid will give us an epoxide. So my favorite, and again, MCPBA will work. But I always use peracetic acid. It's very good peroxy acid. So if I take peracetic acid and add with this alkene, here's what I get. I get this molecule here, which is exactly what we have here. So the synthesis starting from an alkene, we start from here, we get to epoxide. Now remember, we looked at this molecule and said our nucleophile is actually in the more substituted carbon. That means it has to be an acid. This is an ether, so that means that I'm looking at Williamson ether synthesis in an alcohol, right? So if I take ethanol and add in some sort of acid, well, this is in acidic conditions, which means that the first thing is going to happen is that my ether is going to get protonation, oxygen, 3 bonds plus 1 formal charge. And then my nucleophile comes in an attack. Right? Now remember, it's in acidic conditions, so the more substituted carbon. So this oxygen is going to come in, attack the carbon, and kick off the alcohol, which does not leave. It's just bonded to this carbon. So now we have something that looks like this. Right? On this carbon, we have the alcohol that's bonded to an H, and I'm drawing the molecule slightly different with oxygen 3 bonds plus 1 formal charge, and this carbon we have our alcohol. Now again, right, since we're in acid H3O plus, well, we just grab an hydrogen, so we're going to have water in solution now. That's going to act as a base and comes in and neutralize the molecule. So let's draw it like it is. Right, which is exact. So this should be down here. Same thing. Again, one carbonated alcohol, one carbonated alcohol. And this is how we make this molecule. So let's go through a couple more examples to kind of get the concept deep, get it into our head. The first time maybe confuse it. So what if we wanted to make, right? So let's say, okay, we wanted to make this molecule, right? So make this molecule, and the direction says to make from any epoxide. Well, what would be the solution? Well, again, I'm going to retrosynthesize this. Notice that I have an alcohol beside an ether. So again, I'm thinking I'm going to close this ring here to form an epoxide. Right? Now, look at the carbon that's contained in both substituents. Right? This carbon here. Your nucleophile is on the less substituted carbon. Your nucleophile is on the less substituted carbon, which means that this is coming from some sort of base. Your nucleophile is on the less substituted part of the carbon. Right, your nucleophile is on the less substituted part of the carbon. So let's see if we could retrosynthesize this. Well, if I retrosynthesize this molecule, well, what's the bond I'm going to break? Well, I could break this bond and create my epoxide here. So there's my bond. This bond coming down represented this bond, and I'm going to create my epoxide here. All right. Now notice that my ether, my nucleophile is on the less substituted carbon. Right. This is a primary carbon. This OH is on a secondary carbon. Right. So it's on the less substituted carbon, which means that we said epoxides react in acidic conditions and basic conditions, but we said that in bases we get the less substituted carbon. Right. So we could take this molecule and add some sort of ethanol in some sort of base, and we should get a product. So let's synthesize it. So, right, if we take this molecule here, this epoxide here, and we added sodium hydride in some sort of in ethanol, right? Again, sodium hydride deprotonates my oxygen, right? So I'm gonna have this molecule here in solution. Oxygen negatively charged. Now, because we're in basic conditions, it's going to attack the less substituted carbon. So let's see. Comes in, attacks, and kicks off the negatively charged oxygen. So therefore, I have something that looks like this. All right. This carbon, now we have an O that's negatively charged up there. All right. And this carbon is bonded to a carbon that's bonded to a carbon. Well, it's bonded. This carbon is bonded to a carbon. So, yeah, so this carbon is bonded to. Yeah, so I messed that up. So there should be an O. It's bonded to an O that is bonded to another carbon. So again, sorry about that, guys, but let's redo that, right? So again, you can see that my O is bonded to this less substituted carbon. So again, we have 1, 2, we have 3, and this carbon is bonded to my O, which has 2 other carbons to it. All right. So now again, since we're in basic conditions, we're going to have water come in and act as a base and form a neutral product. Right. So again, notice the difference. Anytime we're in basic conditions, look at where your nucleophile is. You got to look at where your nucleophile is attacking to decide, okay, well, is this in basic or is this in acidic conditions? Now let's make this. What if we were given instructions on the exam? Okay, well, I wanted you to make this from any alkene. Any alkene. Immediately I'm thinking about, can I take this alkene? Are you thinking about that too? Can I use this alkene? right? Can I use this alkene? Well, let's try. Well, if I take this and add peracetic acid, well, this should be. So if I take this and add peracetic acid, all right. So if I take this and add peracetic acid, well, I get an epoxide. Yeah. So there's my methyl group, and I get an epoxide. Now, remember we said in acidic conditions, epoxide react, and epoxide, your nucleophile goes on more substituted carbon. So again, you can see that this is my more substituted carbon. So if I take this and add it in HCl, I should get my observed product. Should get an alcohol. So again, these are the typical problems you will see with epoxides, alkenes, all come together. The idea of basic versus acidic conditions for epoxide especially.